We are interested in minimizing this quadratic function. So our variables are in the n-dimensional complex valued x. So x has components, x1, x2, all the way to xn. And these are complex, so each of those variables has a real part and an imaginary part. Matrix A is given, and it is a Hermitian matrix. We will solve for a general matrix A, so it is not necessarily a positive definite. So we'll take all possibilities into account. It is just a Hermitian matrix. And then we have the n-dimensional vector B, which is given. So the optimization variables are the components of vector X. And so in terms of real variables, we have 2n real optimization variables. And those are the real and imaginary parts of the components of vector X. Now, the function that we have is differentiable, so it can be differentiated twice. And the first derivatives are continuous. So we know that a necessary condition for optimality is that the partial derivatives must be equal to 0. So in other words, that if we call this objective function g of x, then if we take the partial derivative of j with respect to the real part of x1, the partial derivative of j with respect to the imaginary part of x1, the partial derivative of j with respect to the real part of x2, and so on and so forth. So we have 2n partial derivatives. So a necessary condition for optimality is that those guys must be equal to 0. And so what we do is that we compute the gradient vector and we equate it to the all 0 vector. And since now our variables are arranged in this n-dimensional vector in the complex space, then we can define our gradient vector in this way. So we will define a gradient vector that is n-dimensional. And basically the first component in the gradient vector is the partial derivative of j with respect to the real part of x1 plus I times the partial derivative of j with respect to the imaginary part of x1. And the second component, partial derivative of j with respect to the real part of x2 plus I times the partial derivative of j with respect to the imaginary part of x2, and so on and so forth. So if we take this gradient vector and if we equate this gradient vector to the all 0 n-dimensional vector, then we are equating each component to 0. And if we have a complex quantity and we equate it to 0, it means that the real part must be equal to 0 and the imaginary part must be equal to 0. Okay, so rather than having a gradient vector that is 2n dimensional, in which we have, let's say, the partial derivative with respect to real x1 and then the partial derivative with respect to imaginary x1 and so on and so forth, we can again construct a gradient vector with the same dimensionality as x, and we can combine the partial derivatives with respect to the real and imaginary parts by the plus I here, and this will do the job for us. By the end of the day, a necessary condition for optimality, if our function is C1, so it is, the first order partial derivatives exist and they are continuous. A necessary condition is that the partial derivatives are equal to 0 at the minimum. Then no problem. I mean, we can just do this trick here and have an n-dimensional gradient vector defined in such a way. And if we equate this gradient vector to the all 0 vector, then we are taking every partial derivative and equating it to 0. And so definitely this will be an important step in the solution. So how can we obtain the components of this vector? So how do we obtain the partial derivatives? Okay, so the tedious way is actually to take this objective function and to write it explicitly in terms of, so this is a quadratic form, so it's a double sum, and then those are inner products, so we can write them as these sums here, and then we can actually write down every xk as a real part and imaginary part, but this will be very tedious. So we can obtain those partial derivatives in what can be deemed as like a more efficient way. So the partial derivative of j with respect to the real part of x sub j, small j here, then from the definition of a partial derivative, we will take vector x and we will perturb basically the jth component of vector x, specifically the real part of the jth component. So here this t is real, and this e sub small j, this is the coordinate vector, or the canonical vector, in which basically it's an all zero vector except that it has 1 in the jth position. Okay, so this is basically the partial derivative. So if you have a function j and it depends on many things, then if you want the partial derivative of big J with respect to the real part, the real part of x small j, then we will take this guy and we will add to it, a t. The other guys are kept constant, and then we subtract the function. Here we have the real of xj. Okay, and then we divide by t, and then we take the limit as t goes to 0. So this is exactly what we are doing here. Take your function, replace each x by x plus t. So t is a real scalar. Ej again is the vector with 1 in the jth component, 0 elsewhere. And so we replace each x by x plus t, and then multiply by this coordinate vector. And then we subtract the function itself. And then we divide by t, and then we take the limit. So note, for example, that when we expand this, we will get x Hermitian ax, and it will go with this guy. We will get from here, for example, minus b Hermitian x, it will go with that guy, and so on. Also, there will be terms that in the numerator, they will have t squared. So, for example, in the numerator, we will get t squared, and then we will get e sub small j Hermitian e sub small j, like this. And then we divide by t in the denominator, so that's t e sub small j Hermitian e sub small j, and then we take the limit as t tends to 0, so this will go to 0 as t tends to 0. So our focus will actually be the terms that are linear in t in the denominator, and so those guys, when divided by t, there will be just numbers, and those will be the result of the limit. Okay, so this is the idea. So for example, I will take from here the Hermitian of this quantity, which is, again, there is a t. If we do things in slow motion, there will be a t, but then it will go with this t in the denominator. So this is Ej Hermitian. We can write it as Ej transpose. Basically, it is a real valued vector. And then we have a multiplied by x. And then we have a term which is x Hermitian, and then a multiplied by e sub small j here. Okay. And from here, the terms that are linear in t in the numerator, so we'll have b Hermitian ej, and then we will have ej Hermitian, or ej transpose times b. And so basically those guys are the result of the limit. And so this quantity here is the partial derivative of j with respect to the real part of x sub small j, which is this index. Small j is an index that goes from 1 to a small n. Now, if we multiply a from the left by a row vector that has just 1 in the jth position and 0 elsewhere, basically the result of this multiplication is a row vector which is specifically the jth row of matrix A. Okay, and if we take b Hermitian ej, so b Hermitian is this vector b1 conjugate, b2 conjugate, all the way to bn conjugate. And then we multiply it from the right by this vector, so we will pick the component bj conjugate. Ej transpose times b, this will give us the jth component in vector b. Okay, and so those are basically so this is the partial derivative of j with respect to the real part of the component x sub small j in vector x, which is the vector of our optimization variables. Now, again, like our problem is indeed, if we think about the optimization problem in terms of real valued variables, then actually we have 2n real variables, the real parts and the imaginary parts. So we also need to take the partial derivative with respect to the imaginary part of x sub j. And in this case, what we will do is that we will do the same thing like here, but we will use it. And so t is our old friend. It is real valued, but it is multiplied by I. So here we are perturbing, we are adding, a t that will tend to 0 to basically to the imaginary part of the jth component of vector x. Okay, so this is what we need to do so that we are basically we write down a limit that is in fact the definition of the partial derivative of big J, which is our objective function with respect to the imaginary part of x, sub small j, which is the imaginary part of the jth component of the the vector of optimization variables x. Now, same story. So in the numerator, there will be terms that are cancelled. For example, x Hermitian ax will go with this guy. B Hermitian x will go with that guy. Minus x Hermitian b. Then here we have plus x Hermitian b. Then we will have quadratic terms. So for example, this, when we multiply this by this, there will be a t squared. No problem. The same story like upstairs here, that basically you have t squared, you divide by t, that's a t. Eventually, you will take the limit as t tends to 0. And so this will go to 0. So, the structure of our objective function here, requires that we only focus on the terms in the numerator that are linear in t, that have a t. And this t actually will go with the t in the denominator. Okay. And so what are the terms of interest? So let's actually write this guy. If we apply Hermitian to this vector, we'll get x Hermitian, and then plus I becomes minus I, and t is a real variable, so its conjugate is itself. And ej Hermitian, I can write it as ej Hermitian, or I can write it as ej transpose. Okay, and so and then the other guy will be the bracket ax plus I, and we don't need the t. We will imagine that the t is already, or let's have it and then eliminate it. And then we'll have plus I, and then we have t, and then we have a times eg. Okay. So again, when we expand, x Hermitian ax will go with this guy. There will be a term with t squared, divide by t, there it will be a term, something multiplied by t, it will go to 0. So the terms of interest will be I t x Hermitian a e sub small j, and then minus I t e j transpose a x. And then when we divide by t, those are basically the survivors. So minus I e sub small j transpose ax plus I x Hermitian a times e sub small j. So that's again the canonical vector with 1 in the jth component, 0 elsewhere. And then again, we can do the same for the other, for these two guys here, and we will get these two terms. And we can write, so we have ej transpose times a. This will give us the jth row, then eta multiplied by x. But like if here and here we have a, and then we have ej multiplied by a from the right, then this will give us the jth column in matrix A, and so on. Now again, our trick will be we need those partial derivatives for a specific mission. The mission is to take each one of them and equate to 0. Okay, and so we get the exact same effect if we actually combine the two partial derivatives after multiplying this partial derivative by plus I, and then we take this complex valued quantity and set it equal to 0, because when we set it equal to 0, then this partial derivative will be 0 and that partial derivative will be 0. Of course, what I am saying, it has an implicit assumption, which is that actually each of those partial derivatives is purely real. Each of those partial derivatives is purely real, and this is actually the case. And for example, you could check, this partial derivative here, you have this guy, and then you have its complex conjugate, and then you have the complex conjugate. And now what about this and that? They are in fact the complex conjugate of one another. Okay, and the reason for this is that, I mean, so what is this quantity here? This quantity here is summation AJV, for example, and then XV, and V is from 1 to N. So what about this guy? So this guy is summation V from 1 to N, then we have XV conjugate, and then we have this. These are the elements of the jth column in A. So this is AJ, sorry, AVJ, okay, because the J is now the index of the column, so the column index is J and then V, and this is the element, you know, the element, the Vth element in the Jth column of A. Now, don't forget that we are working with a very special matrix. Our matrix is a Hermitian matrix. It is Hermitian, and because it is Hermitian, then this guy here is equal to AJV conjugate. And so basically this sum here is the complex conjugate of this sum there. Okay, so if this is a concern, I mean, when I say that we'll take this, you know, this sum and equate it to 0, so the real part is equal to 0, imaginary part is equal to 0, it's as if we are taking each partial derivative and equating it to 0. It's because each partial derivative is indeed purely real. Whenever you see something that looks like it can be complex value, then it is, you know, it comes together with its complex conjugate. Okay. So if we combine the partial derivatives with respect to the real and imaginary parts, we will take this first and multiply it by I, and then when we combine, you know, we will get basically this result here. That you know, this the jth component in the gradient vector as defined above is basically, it is 2 times the jth row of matrix A times the column containing the optimization variables, the x vector, minus 2, and then here we have the jth component of vector B. Okay, and so if we take those partial derivatives, you know, combined in this way and stack them on top of one another, then we end up with 2 times A times, so the matrix A times vector x minus 2b, which is the result that we have. You can obtain the partial derivatives any way of your choice. Okay, the most important thing to get the partial derivatives correctly, equate all of them to 0, and you know, then we will get that basically you know, we need to satisfy that AX is equal to B if we can. So keep this in mind. You know, in the typical case, A, matrix A will be not just Hermitian, but Hermitian and positive definite. And in that case, there is a unique solution, you know, that I will talk about, and it is simply the inverse of A times B. The inverse of A times B, just based on this equation, you know, if A is positive definite, then it is invertible, and so X is A inverse B, and then we can show that actually it is the unique optimal solution to our minimization problem. But you know, basically we are trying to be general here and to sweep through all the possibilities of matrix A. So let's go first not to the sweet case in which A is Hermitian and positive definite, but to the case in which A has at least one negative eigenvalue. So A has one negative eigenvalue or more. So in that case, the claim is that the objective function here, if A has one or more negative eigenvalues, this objective function is unbounded below, which means that we can make the objective function, which is big J, we can make big J approach negative infinity. Okay, so how can to show something like this? So suppose that A has basically an eigenvalue lambda, and this eigenvalue lambda is strictly negative, and the associated eigenvector is Q. Now what we will do is that we will let X be some positive number times the eigenvector Q. Again, not an arbitrary eigenvector, it's the eigenvector associated with the strictly negative eigenvalue. Then take this X and insert it in the objective function. So X Hermitian will be alpha, then Q Hermitian. So that's X Hermitian. Then we have A, and then X will give us another alpha, and then we have Q. So this will be the quadratic term, and AQ is equal to lambda Q, and so this will be lambda alpha squared, and then Q Hermitian Q, and Q Hermitian Q is the L2 norm squared of vector Q. Okay, and then do the same in the linear terms. So B Hermitian X, again, we will replace X by alpha Q and X Hermitian by alpha Q Hermitian. Again, alpha is a positive real number. And so this is basically the objective function if X is put in this form. It's a vector that is proportional to basically the an eigenvector associated with the strictly negative eigenvalue. Now, take alpha as a common factor. Take alpha as a common factor, and we will get something like this. Can we make J go to minus infinity as alpha goes to plus infinity? Yes. And the reason is, this bracket here can be made negative by choosing an alpha that is large enough. Okay, and so can we make this bracket negative? Here is alpha lambda, the L2 norm of vector Q minus P Hermitian Q plus Q Hermitian B. Can we make this thing less than 0? Well, move this to the other side. So alpha lambda, the L2 norm squared of Q, is strictly less than P Hermitian Q plus Q Hermitian B. Okay, and then divide by the L2 norm squared of Q. Note that Q is an eigenvector, so by definition it's not the odd zero vector, and so its norm is strictly positive. And then divide by lambda, but lambda is strictly negative. So when we divide by this product lambda times the L2 norm squared of vector Q, then basically the inequality will be reversed because we are dividing by a strictly negative quantity. So alpha is strictly greater than, and then we have B Hermitian Q plus Q Hermitian B. Note that this is a real number, can be positive, can be negative, and then we have those guys living happily in the denominator. And so alpha must be greater than this. Now if this quantity is negative, then we need to choose any alpha, any positive alpha. If this quantity is positive, we need alpha to exceed that quantity. So if we choose alpha to be greater than the maximum of 0 and of this quantity here, then this bracket will be strictly negative, and this alpha is strictly positive. The product is strictly negative. And the product actually is a function of alpha. So by pushing alpha towards plus infinity, note that the bracket here, will become more and more negative. So basically J will tend towards minus infinity, indicating that our optimization problem is unbounded below. So this is the first case. So matrix A is a Hermitian matrix, okay? And because it is a Hermitian matrix, its eigenvalues are guaranteed to be real valued. So the eigenvalues are real valued. There are no doubts. This is a theorem. There are no doubts about this. But the question is, do we have negative eigenvalues? If we have one negative eigenvalue or more, then we can make this objective function tend towards negative infinity by choosing vector x to be in the direction of an eigenvector basically associated with a negative eigenvalue of A. This is the first case. Now, if we exclude this case, then now our pool of eigenvalues, contains either 0 or positive or strictly positive eigenvalues. So case 2 will be the sweet case. So case 2 is this case like, in which A is positive definite. Okay, so all the eigenvalues are strictly positive. The determinant is strictly positive. It's non-zero. A is non-singular. It is invertible, and X is equal to A inverse B. And this solution, and we can check that actually the Hessian matrix of the objective function in this case will be a positive definite, and so this is the solution. Okay, and we can take this X and put it back in the objective function to get what is the minimum value of big J. It will be minus B Hermitian A inverse B. So this is the case in which all the eigenvalues are strictly positive. So now we need to account for the fact that perhaps some eigenvalues are positive and some eigenvalues are zero. So in this case, A is positive semi-definite with one or more zero eigenvalues. In this case, the determinant is equal to determinant of matrix A is equal to 0, and A is not invertible anymore. It's not invertible. So this case actually is divided into two subcases, or you can consider them two different cases, depending on your taste. So in one of them, so we have one eigenvalue that is equal to 0 or more, and note that the stationarity condition requires that AX is equal to B. So this is what we get when we take the partial derivatives and equate them to 0. Now, is there a solution? Even if A is not invertible, yes, there is a solution if B is in the range of A, because this equation here, it means that I can take vector B in the n-dimensional space and I can write it as a linear combination of the columns of matrix A. And the coefficients of the linear combination are basically the elements of X. So vector B, note that vector B is given. Okay, so we do not control this. So perhaps matrix A is positive semi-definite with one or more zero eigenvalues, and B is in the column space of A, or B is in the range of A. Okay. In that case, there is a solution. Why? Because if B is in the range of A, then yes, I can write this down. I can find an X. Actually, I can find infinitely many vectors X such that basically this equation is satisfied. And so this is the general solution. So X is not, of course, not the inverse of A, because the inverse is not defined here, because A is singular, but X is the Moore-Penrose pseudo inverse of A, okay, which is denoted like this one, times B, and then we can add to this quantity here. We can add any vector from the null space of A. Note that since A is singular, then its null space is non-trivial. So its null space, it's not just the all zero vector. So if you can take this guy and add any vector from the null space of so basically I forgot it. So V is in the null space of A, and this will satisfy the solution. Check that. If you take A and multiply it by this pseudo inverse of A times B plus a vector from the null space of A, what will we get? We will get this plus AV. Well, V is in the null space of A, so this is the all zero vector, so go away. And then we will have A times the Moore-Penrose pseudo inverse of A times B. Okay, and this is the matrix that orthogonally projects onto the range of A, or onto the column space of A. Okay, which means that if vector B is indeed in the range of A, then this matrix times vector B will give vector B itself. Okay, so if you know about what generally, if I give you a matrix A And matrix A, it can be any matrix, even rectangular matrix, and so on. What is the projection matrix that will take any vector, any vector with a dimensionality that is the same as the dimensionality of the columns of matrix A, and it will basically project this vector orthogonally onto the column space of A. It is A times the pseudo inverse of A, the Moore-Penrose pseudo inverse of A. So this projection matrix, if B itself, and this is our assumption here, is in the range, then basically its a projection is itself, is exactly itself. And one way of seeing this is that what does it mean that B is in the range of A? It means that B can be written as a linear combination of the columns of A. So there exists some vector gamma such that B is A gamma. This is the meaning that vector B is in the range of A. And then we know from the properties of the Moore-Penrose pseudo inverse that basically, I mean, remember that there are the four properties of the pseudo inverse, that this is one of them, that A times the pseudo inverse of A times A, this should give you A. And the pseudo inverse times A times the pseudo inverse, this should give you the pseudo inverse. And it must be the case that A times the pseudo inverse and the pseudo inverse times A, those must be Hermitian. These are basically the four properties that define the Moore-Penrose pseudo inverse. Okay, and so if B is in the range, then I can write down B as A times some given vector, and so we get this thing here. By definition, this is equal to A, and so we get A gamma, and A gamma is B itself. Okay, or again, like if we know or recall basically this, that this matrix is indeed a projection matrix, then this is another way to see that in fact every vector written as the pseudo inverse of A times B plus a vector from the null space of A is indeed a solution to basically this equation, which came from equating the partial derivatives to 0. Okay, so the difference between these two cases. So here in the positive definite case, there is a minimum, and the minimum can be computed. It is this one, but the solution is unique. There is just one solution given by the actual inverse of A times B. But if A is positive semi-definite, and this is very important, and B is living in the column space of A, then we have infinitely many solutions. Can be written all of them can be written as pseudo inverse of A times B plus a vector from those vectors residing in the null space of A. And then we can take this this expression for x, and we can insert this expression in the objective function to get what is basically the minimum objective that we achieve, using this x vector. Okay, and basically I will skip this, and what we get is something that is exactly like this one, but the inverse of A is replaced by the pseudo inverse of A. Okay, so the last case, the fourth and last case, is again a case in which matrix A is positive semi-definite. One or more zero eigenvalues, indicating that A is singular, non-invertible, but now B is not in the range of A. Okay, which means that there is no solution. There is no solution to this. I cannot make the partial derivatives or equal to 0. Okay, so now if you hear something like this, you say, well, then perhaps the objective function is unbounded below, and this is the case, right? Because we cannot actually satisfy, this. We cannot find an x vector such that this is satisfied, because matrix A and vector B are given, and it just it is just the case that B is not in the column space of A, which means that B can never be expressed as A times any n-dimensional vector. So this is the case, and let's show actually how we can derive the objective function big J towards minus infinity. So vector B is not in the range of A. So vector B, let's suppose that it has two components. One component is in the range of A, or the column space of A, but then there is a non-zero component, and this non-zero component is orthogonal to the range of A. Okay, so B is not in the range of A. It means that B can be decomposed into two parts. One part is living in the range of A, but there is a non-zero part that is in the subspace that is orthogonal to the range of A. And this subspace that is orthogonal to the range of A is exactly the null space of A Hermitian. And because our matrix is a Hermitian matrix, so A Hermitian is equal to A. And so the null space of A Hermitian is the null space of A. So this means that since vector B is not in the range of A, then vector B has two components. One of them is in the range of A, and the other component is in the null space of A, which for our Hermitian matrix, is a subspace that is orthogonal to the range of A. Now let vector X be a factor, a positive real number, times B2, times this component of vector B that is not in the range of A, but that is in fact in the null space of A. Now, the quadratic term X Hermitian AX, because X is proportional, X is a positive number times B2, and B2 is in the null space of A. So X itself is in the null space of A, and AX is equal to the all zero vector. So the quadratic term will disappear. And then what about the two terms? So we have these two guys. So we have, this is vector B, and we will take X to be alpha, which is this positive real number, and then B2, and then here we will have alpha B2 Hermitian, and then B1 plus B2. So this is what we get for the objective function. Note that B2 and B1 are orthogonal to one another, so the inner product is equal to 0. So this time is that 0, and this time is that 0. So we are left with minus alpha, and then the L2 norm squared of vector B2. And from here, we will get a similar term, minus alpha, and then the L2 norm squared of vector B2. And so this is minus 2 alpha, and then the L2 norm squared of vector B2. This is strictly positive because our vector is a non-zero vector. And so by pushing alpha towards plus infinity, the objective function will be pushed towards minus infinity. So J is unbounded below.